In this final outcome, we learn to predict the three-dimensional shapes of simple molecules, using electron-pair repulsion to work out both the shape and the bond angle. Let's dive in. Let's set the scene. Molecules are three-dimensional objects, not flat drawings on paper, and the arrangement of their atoms in space is what we mean by molecular shape. That shape controls polarity, reactivity, and physical properties, so it's well worth predicting. We'll do that with a simple, reliable model called electron-pair repulsion theory, often abbreviated to VSEPR, and you'll learn to name the shapes and state their bond angles. Why does shape matter so much? Well, the bent shape of water is what gives it its unusual properties. Carbon dioxide is linear, which is part of why it's a non-polar gas. In biology, enzymes recognize their substrates by precise three-dimensional shape, and drug molecules must fit a receptor like a key in a lock. So being able to predict shape lets us explain and even predict how a molecule behaves. And reassuringly, shape follows directly from the arrangement of electrons. Here's the core idea in a nutshell. Electrons carry negative charge, so pairs of electrons repel one another. Around a central atom, those pairs spread out as far apart as they possibly can, which minimizes the repulsion and gives the most stable shape. So our method is simply this. Count the pairs, then place them to maximize their separation. The positions of the bonded atoms then define the shape. That's the whole of the valence shell electron-pair repulsion model. Some quick definitions. A bonding pair is a shared pair of electrons, forming a covalent bond between two atoms. A lone pair is a pair of outer electrons on the central atom that isn't used in bonding. Electron-pair repulsion is the idea that electron pairs move apart to minimize repulsion. And a bond angle is the angle between two bonds meeting at the central atom, measured in degrees. Let's set out the method for counting electron pairs. First, identify the central atom, usually the one written first, or the least common one. Find how many electrons are in its outer shell, which is its group number. Add one electron for each atom bonded to it. Then divide the total by 2 to get the number of electron pairs. The bonding pairs equal the number of bonded atoms, and the lone pairs are simply the total pairs minus the bonding pairs. There are 5 shapes to know in this unit. Linear, 2 bonding pairs, no lone pairs, 180 degrees. Trigonal planar, 3 bonding pairs, no lone pairs, 120 degrees. Bent, 2 bonding pairs with 1 or 2 lone pairs, less than 120 degrees. Pyramidal, 3 bonding pairs, 1 lone pair, 107 degrees. And tetrahedral, 4 bonding pairs, no lone pairs, 109.5 degrees. The number of pairs sets the basic geometry. Let's connect the number of pairs to the base geometry. 2 pairs arrange themselves linearly, giving an ideal angle of 180 degrees. 3 pairs arrange trigonal planar at 120 degrees. 4 pairs arrange tetrahedrally at 109.5 degrees. In general, the more pairs there are, the further they push apart. And then, as we'll see, any lone pairs reduce these ideal angles slightly. Let's start with linear molecules. Here, the central atom has 2 bonding regions and no lone pairs. The 2 bonds point in exactly opposite directions, giving a straight line with a bond angle of 180 degrees. Carbon dioxide is a good example, where carbon has 2 double bonds to oxygen. So is beryllium chloride, with 2 single beryllium-chlorine bonds. And note, a double bond counts as just 1 bonding region when we work out the shape. Let's predict the shape of carbon dioxide. The central atom is carbon, forming 2 double bonds to oxygen. Each double bond counts as 1 region of electron density, so there are two bonding regions and no lone pairs on the carbon. Two regions repel to point in opposite directions, and that maximum separation gives a linear arrangement. So carbon dioxide is linear, with a bond angle of 180 degrees. Next, trigonal planar molecules. Here, the central atom has three bonding regions and no lone pairs. The three bonds spread out into a flat triangle, with all the atoms in one plane and angles of 120 degrees. Boron trifluoride is the standard example, with three boron fluorine single bonds. Because the three regions repel equally, you get three identical 120-degree angles. Let's work out boron trifluoride. Boron is the central atom, in group 3, so it has three outer electrons. It bonds to three fluorine atoms, so we add 3 electrons, giving a total of 6. 6 divided by 2 is 3 electron pairs, and all 3 are bonding pairs, with no lone pairs left on boron. 3 bonding pairs repel equally into a flat triangle. So boron trifluoride is trigonal planar, with bond angles of 120 degrees. Now, tetrahedral molecules. The central atom has 4 bonding regions and no lone pairs. 4 pairs can't lie flat, so they point towards the 4 corners of a tetrahedron, giving the ideal bond angle of 109.5 degrees. Methane is the classic example, with 4 identical carbon-hydrogen bonds. Carbon tetrachloride and the ammonium ion share the same shape. Tetrahedral is the key shape for carbon compounds, so it's well worth knowing. Let's predict methane's shape. Carbon is central, in group 4, with 4 outer electrons. It bonds to 4 hydrogen atoms, so we add 4, giving a total of 8 electrons. 8 divided by 2 is 4 electron pairs, and all 4 are bonding pairs, with no lone pairs on the carbon. 4 equal pairs spread out to the corners of a tetrahedron. So methane is tetrahedral, with bond angles of 109.5 degrees. Now for an important refinement, the effect of lone pairs. A lone pair is held closer to the central atom than a bonding pair, and because of that, it repels more strongly. The order of repulsion runs: lone pair to lone pair is strongest, then lone pair to bonding pair, then bonding pair to bonding pair. So each lone pair squeezes the bonding pairs a little closer together, reducing the bond angle by roughly 2.5 degrees per lone pair. And we always name the shape from the atom positions, not from the lone pairs. Let's look at pyramidal molecules. Here we have 4 electron pairs, 3 bonding and 1 lone pair. The 4 pairs still adopt a tetrahedral arrangement, but we only see the 3 bonded atoms. The lone pair pushes the bonds downward into a pyramid shape, and its extra repulsion trims the angle from 109.5 down to about 107 degrees. Ammonia is the textbook example. Let's predict ammonia. Nitrogen is central in group 5. With 5 outer electrons, it bonds to 3 hydrogens, so we add 3, giving a total of 8 electrons. 8 divided by 2 is 4 pairs, made up of 3 bonding pairs and 1 lone pair. The 4 pairs arrange tetrahedrally around nitrogen, but the lone pair repels more strongly, squeezing the hydrogen-nitrogen-hydrogen angle. So ammonia is pyramidal, with a bond angle of about 107 degrees. Now bent molecules from 4 pairs. Here we have 2 bonding pairs and 2 lone pairs. Again, the 4 pairs take up a tetrahedral arrangement, but only 2 bonded atoms are visible, which gives a bent shape. With 2 lone pairs repelling strongly, the angle closes further, falling from 109.5 to roughly 104.5 degrees. Water is the classic example. Let's predict water and see why its angle is smaller than ammonia's. Oxygen is central in group 6 with 6 outer electrons. It bonds to 2 hydrogens, so we add 2, giving a total of 8 electrons. 8 divided by 2 is 4 pairs, made up of 2 bonding pairs and 2 lone pairs. The 4 pairs arrange tetrahedrally around oxygen, but 2 lone pairs repel more than the single lone pair in ammonia. So water is bent, or V-shaped, with a bond angle of about 104.5 degrees, smaller than ammonia's 107. Let's gather the tetrahedral family together, because it's such a neat illustration. Methane has 4 bonding pairs and no lone pairs. Ammonia has 3 bonding pairs and 1 lone pair. Water has 2 bonding pairs and 2 lone pairs. All 3 start from the same tetrahedral arrangement of 4 pairs, but the resulting shapes differ. Methane is tetrahedral at 109.5 degrees, ammonia is pyramidal at 107, and water is bent at 104.5. The pattern is clear. More lone pairs mean a smaller bond angle. Let's check your understanding. First, how many bonding and lone pairs are on the central atom in ammonia? Second, why is the bond angle in water smaller than in methane? And third, explain why carbon dioxide is linear, even though carbon forms 4 bonds. Have a think about each. Now a subtler case, a bent shape arising from 3 electron regions rather than 4. If you have 2 bonding regions plus 1 lone pair, you again get a bent molecule, but the base arrangement this time is trigonal planar at 120 degrees. The single lone pair reduces the angle to about 118 degrees. Sulfur dioxide is the example. The lesson is always the same. Count the regions first, then subtract the lone pairs. Let's predict sulfur dioxide. Sulfur is central and bonds to 2 oxygen atoms. There are 3 regions of electron density on the sulfur, made up of 2 bonding regions and 1 lone pair. 3 regions give a trigonal planar base at 120 degrees, but the lone pair pushes the 2 bonds slightly closer together. So sulfur dioxide is bent with a bond angle of about 118 degrees. Let me give you a reliable routine to follow every time. Step 1. Identify the central atom. Step 2. Count the total electron pairs around it. Step 3. Split them into bonding pairs and lone pairs. Step 4. Place all the pairs as far apart as possible. Step 5. Name the shape from the atom positions only. And Step 6. Adjust the angle downward for each lone pair. Follow those 6 steps, and you'll rarely go wrong. A final round of terms. Tetrahedral means 4 bonding pairs pointing to the corners of a tetrahedron at 109.5 degrees. Pyramidal means 3 bonds and 1 lone pair, forming a pyramid at about 107 degrees. Trigonal planar means 3 bonding pairs in a flat triangle at 120 degrees. And VSEPR stands for valence shell electron-pair repulsion, the model we've used throughout to predict shape. One last check. First, state the shape and bond angle of boron trifluoride and explain your reasoning. Second, rank lone-lone, lone bond and bond-bond repulsion from strongest to weakest. And third, predict the shape of beryllium chloride and give its bond angle. Work those through to round off the unit.